Chapter 10, Module 1. Mayer-Vietoris Theorem provides a very important tool for computing singular homology groups. In this module, we shall establish Mayer-Vietoris Theorem. For proving Mayer-Vietoris Theorem, we have to establish 3 exact sequences, and we shall show how we can join them to get a long exact sequence called Mayer-Vietoris sequence. Let us recapitulate a few facts. Suppose X is a topological space. If Cnx is the free abelian group generated by the collection of all singular n simplexes Snx for each dimension n greater than equal to 0, then we define a map delta n from Cnx to Cn minus 1x given by delta nf equal to summation I equal to 0 to n minus 1 to the power of I f composed di. These functions delta n are called boundary homomorphisms. Here di is a map which inserts 0 after the ith coordinate of any n minus 1 tuple. For each n greater than equal to 1, Znx stands for the kernel of delta n for each n greater than equal to 0, and Bnx stands for the image of delta n plus 1, and we know that these two are subgroups of Cnx. We take Z0x as C0x, and it can be observed that Bnx is a subset of Znx for all n greater than equal to 0. We also define something called the homology group Hnx as the quotient group Znx by Bnx for every n greater than equal to 0. Suppose x and y are two topological spaces and f is a continuous function from x to y. If Snx and Sny denote the collection of all singular n simplexes of x and y, then Cnx and Cny are the corresponding free abelian groups generated by Snx and Sny respectively. For every S belonging to Snx, there exists F composed S in Sny, and we get a map from Snx to Sny by sending the element S to the element F composed S. Extending it by linearity, a homomorphism Cnf from Cnx to Cny is obtained. It can also be seen that the diagram shown here is commutative. That means Cn minus 1f composed delta n is equal to del n composed Cnf. We have also seen earlier that Cnf takes all the n cycles of x to the n cycles of y, and Cnf sends the n boundaries of x to the n boundaries of y. So, for each n greater than equal to 0, the continuous function f from x to y induces a homomorphism Hnf from Hnx to Hny, which is given by the formula that Hnf evaluating at z plus Bnx gives the element Cnfz plus Bny. Now, we shall use all these notations that whenever we say capital X, we always mean that it is a topological space. If U and V are taken, then they always mean open subsets of X with X equal to U union V, unless we state otherwise. The maps I, J, K and L are respectively the inclusion maps from U to X, V to X, U intersection V to U, U intersection V to V. From these inclusion maps, we get the induced homomorphisms H n I, H n j, H n k and H n l for every n greater than equal to 0. Now, we define two functions. One is f n from the direct sum H n u and H n v to the homology group H n x, which we define by f n evaluated at a point x y is equal to H n I x minus H n j y. And another map G n from H n u intersection v to H n u direct sum H n v, and it is defined by G n x is equal to H n k of x comma H n l of x. In what follows, for ease of notation, we shall denote these maps by f and g instead of f n and g n, and understand the domain from the context. Let us state a result that is known as chain splitting without proof. We shall use this result frequently in this module. If S is a member of C n x and capital X is U union V, where U and V are open sets in X, then there are SU and SV respectively in CNU and CNV such that S is homologous to SU plus SV. That means, there is some chain T in Cn plus 1x such that S minus SU minus SV is equal to delta n plus 1 of T. It is easy to observe that the composite H n I composed H n k is equal to H n j composed H n l. That means, the following diagram commutes. Since the diagram commutes, if we take f of g x for any x from the domain of G, then that is equal to f of H n k x comma H n l x, and that is equal to H n I of H n k x minus H n j of H n l x. But since the diagram commutes, we have that this difference is equal to 0. That means, f compose G of any x is equal to 0, so that image of G is contained in kernel of f. Now, with this observation, we establish our first exact sequence, that for each n greater than equal to 0, H n u intersection V to h n u direct sum h n v to h n x, if we take this sequence, then we already have defined the maps G and F between these two groups h n u intersection v and h n u direct sum h n v, and h n u direct sum h n v and h n x. We have to show that this sequence is exact. For this to be exact, we need to show that kernel of f is equal to image of G. In the observation, we have already seen that image of G is contained in kernel of f. So, we want to show the reverse inclusion. That means, we take a point C D from kernel of f and wish to show that it is a member of image of G. Since C D is in kernel of f, C is in h n u and D is in h n v, such that f of C D is equal to 0. Now, suppose alpha and beta are cycles that represent C and D respectively. Now, f of C D is equal to 0 implies h n I C minus h n j D is the null element of h n x, so that there exists some t in C n plus 1 x with C n I alpha minus C n j beta is equal to delta n plus 1 of t. By chain splitting, there are chains T u in C n plus 1 u and T v in C n plus 1 v, such that T is homologous to T u plus T v. So, T minus T u minus T v is equal to delta n plus 2 of A for some A belonging to C n plus 2 of x. That is, delta n plus 1 T minus T u plus T v is equal to delta n plus 1 of delta n plus 2 of A, and that is equal to 0, because deltas are all boundary homomorphisms. Therefore, we get that delta n plus 1 of t is equal to delta n plus 1 of T u plus delta n plus 1 of T v. Hence, delta n plus 1 of T u plus delta n plus 1 of T v is equal to C n I of alpha minus C n j of beta, and that is equal to alpha minus beta. From this we get alpha minus d n plus 1 T u is equal to beta plus d n plus 1 T v. Now, the n chain on the left of the expression is a chain on u, and the n chain on the right of the expression is a chain on v. So, this last equation suggests that alpha minus delta n plus 1 of T u and beta plus delta n plus 1 of T v are chains of u intersection v. So, let us write it as some element x, that means alpha minus delta n plus 1 T u, which is equal to beta plus delta n plus 1 of T v, is equal to some x, where x is a chain in u intersection v. Consequently, C can be written as alpha plus b n u, which is alpha minus delta n plus 1 of T u plus b n u, and that is equal to x plus b n u, which is h n k of x plus b n u intersection v. Similarly, the element D is of the form H n L of x plus B n u intersection V. Hence, the pair C D is equal to G of x plus B n u intersection V, that is, the pair C D is in image of G. Therefore, as we claimed earlier, kernel of F is a subset of image of G, proving the sequence as an exact sequence. So far, we have defined maps between the homology groups of the direct sum of H n u, H n v and H n u intersection v, and also connecting H n u intersection v with H n x. Now, we shall see how we can define a map that connects homology groups of different dimensions. So, we start with defining a map which takes the elements of H n x to the homology group H n minus 1 of u intersection v. We define a map from H n x to H n minus 1 of u intersection v. So, let us take an element C from C n x such that C plus B n x is an element of H n x. That means, C is a cycle and therefore, delta n of C is equal to 0. By chain splitting, there exists C u in C n u and C v in C n v such that C minus C u minus C v is equal to delta n plus 1 of t for some t belonging to C n plus 1 of x. So, delta n of C minus C u minus C v is equal to delta n of delta n plus 1 of t, and that is equal to 0. So, that is delta n of C, which is equal to 0, is equal to delta n of C u minus C v, which gives delta n of C u is equal to minus delta n of C v. The left side of this expression shows that it is a chain in U, and the right side of the expression shows that it is a chain in V. Hence, both are chains in U intersection V. Also, delta n of C u is a member of C n minus 1 of U intersection V with delta n minus 1 of delta n C u is equal to 0, which implies that delta n C u is a member of Z n minus 1 U intersection V. Hence, for each C plus B n x belonging to H n x, we find an element delta n C u plus B n minus 1 of U intersection V inside H n minus 1 of U intersection V. It is not hard to show that such an element depends on C only and not on any choice of the element C u. We state it as a lemma. It can be seen very easily that if C is homologous to C u plus C v and also to B u plus B v, where C u and B u are in C n u and C v and B v are in C n v, then delta n of C u plus B n minus 1 of U intersection V is equal to delta n of B u plus B n minus 1 of U intersection V. With the help of that lemma, we get a map that between H n x and Hn minus 1 u intersection v for every n greater than equal to 1, which is described by the element C plus Bnx is sent to the element delta n of Cu plus Bn minus 1 of u intersection v, where Cu is an element of Cnu as discussed before. Now, before establishing our next exact sequence, we observe a very important fact, that if C plus Bnx is an element of Hnx, then delta Nc is equal to 0, and applying the chain splitting on the element C, there exists Cu and Cv such that C minus Cu minus Cv is of the form delta n plus 1 of t, where t is in C n plus 1 of x. So, delta n evaluated at the point C minus Cu minus Cv is equal to delta n on delta n plus 1 of t, which in turn gives that delta Nc minus delta Ncu minus delta Ncv is equal to 0. Hence, delta Ncu is equal to minus delta Ncv. The left side expression is a chain on u and the right side expression is a chain on v. Therefore, both are members of Pn minus 1 u intersection v. This piece of argument is utilized very frequently in what follows next. We want to establish that the sequence of groups and homomorphisms as written here, that is Hnu direct sum Hnv to Hnx is a map F, and Hnx to Hn minus 1 of u intersection v is a map eta. This particular sequence is exact. Let us choose any point x from image of F. We wish to show that it is in the kernel of eta. Since x is in image of F, there exists C bar and D bar in Hnu direct sum Hnv such that f of C bar D bar is equal to x. Now, eta x is equal to eta of f of C bar D bar, and that is equal to eta of Hni C bar minus Hnj D bar. And Hni C bar is a member of Hnx, implies that it is of the form alpha plus Bnx, where alpha is an n cycle. Using chain splitting on alpha, we get alpha u and alpha v such that alpha u plus alpha v is homologous to alpha. As observed earlier, delta n alpha u is an element of Bn minus 1 u intersection v. Similarly, delta n beta u is an element of Bn minus 1 u intersection v, where Hnj d bar is of the form beta plus Bnx, and beta is homologous to beta u plus beta v. Then eta x is of the form delta n alpha u minus beta u plus Bn minus 1 u intersection v, and that is equal to Bn minus 1 u intersection V, proving that x belongs to kernel of eta, that is image of f is contained in kernel of eta. For the reverse inclusion, we start with C plus Bnx from kernel of eta. Using chain splitting on C, we have Cu plus Cv homologous to C, then delta n of Cu is in Bn minus 1 u intersection V, and proceeding exactly as the previous observation, delta n Cu is equal to delta n d for some d belonging to Cn u intersection V, and that is equal to minus delta n Cv, and hence Cu minus d is in kernel of delta n and Cv plus d is in the kernel of delta n. So, Cu minus d belongs to Cnu and Cv plus d belongs to Cnv, with their sum equal to Cu minus d plus Cv plus d implies that C is homologous to Cu minus d plus Cv plus d. Hence, if operated on this element Cu minus d plus Bnu, comma, minus Cv plus d plus Bnv becomes C plus Bnx, that is C plus Bnx is an element of image f. Finally, we establish the last exact sequence that maps Hnx to Hn minus 1 u intersection V via eta and maps Hn minus 1 u intersection V to the direct sum Hn minus 1 u with Hn minus 1 V via the map G, and we shall show that this is an exact sequence. So, take any point from Hnx, let us call that point x plus Bnx, then G composed eta evaluated at x plus Bnx is equal to G of delta n xu plus Bn minus 1 u intersection V, where xu is the thing that we have mentioned earlier, that is the component of x within Cnu, which is added with another component xv of Cnv gives an element homologous to x. And simply by applying the functions, we ultimately get that G composed eta on x plus Bnx is equal to the 0 element, that is image of eta is contained in kernel of G. Now, if we start with an element from kernel of G, then G of that element is equal to the 0 element of the domain of G, that means Bn minus 1 u comma Bn minus 1 v, and so applying the definition of the function G on x bar, we get that x plus Bn minus 1 u is equal to Bn minus 1 u and x plus Bn minus 1 v is equal to Bn minus 1 v, so that x is an element of the intersection Bn minus 1 u with Bn minus 1 v. So, there are elements Bu and Bv respectively from Cnu and Cnv such that x is del n Bu plus del n Bv. Then of course, del n Bu minus Bv is equal to 0, and so Bu minus Bv belongs to Znx. That is, eta operated on Bu minus Bv plus Bnx is equal to x plus Bn minus 1 of U intersection V. Therefore, the element x plus Bn minus 1 U intersection V, which we had started with, is an element of image of eta, proving that kernel of G is contained in image of eta. With all these exact sequences, if we join suitably, we get a long exact sequence called Mayer-Vietoris sequence as shown here. That if X is a topological space, U V are open subsets of X with X equal to U union V, then we get a long exact sequence H n U intersection V to the direct sum H n U direct sum H n V to H n x etc. up to the 0 level H 0 U intersection V to H U direct sum H V to H 0 x to 0. This is a very important sequence known as Mayer-Vietoris sequence. In the next module, we shall see how we shall use this Mayer-Vietoris sequence to compute singular homology groups. With this, we end chapter 10, module 1.